Hello everyone. Welcome to the next section, Boosting Your Database. In this section, we will explain what statistical boosting is, how it works, and introduce the notion of using statistical boosting to better understand data in a database. Now we move on to the first video of this section, Definition and Purpose. We will look at definition and purpose of statistical boosting in this video. First, we will consider a common definition you may find online. Boosting is a machine learning ensemble meta-algorithm for primarily reducing bias, and also variance in supervised learning, and a family of machine learning algorithms which convert weak learners to strong ones. Before we head into the details behind statistical boosting, it is imperative that we take some time here to first understand bias, variance, noise, and what is meant by a weak learner and a strong learner. Let's start out with a discussion on the statistical bias. A statistic is biased if it is calculated in such a way that it is analytically dissimilar to the population parameter being estimated. One of the best explanations for bias that I've come across is the concept of a scale that is off zero by a small amount. In this scenario, the scale will give slightly overestimated results. In statistics, data scientists need to recognize that there are actually several categories that are routinely used to define statistical bias. Bias can arise in various ways, and, as a data scientist, one must be familiar with these occasions. Actually, bias can be introduced to a statistical project at any time or phase. One of the most common times that bias is introduced is at the very start or beginning of a project when data is collected or selected. This is the worst, as almost every effort and all work completed afterwards will be suspect or, most likely, incorrect. Bias data collection. A major source of bias is the way data is collected. Some of the things to look for in data collection methods are 1. Surveys that are constructed with a particular slant or emphasis. 2. Choosing a known group with a particular background to respond to a survey. 3. The reporting of data in misleading categorical groupings. 4. Non-randomness sample selection. 5. Systematic measurement errors. Bias sample selection. The process of sample selection or sampling is also subject to the introduction of bias. Sample bias occurs when the sample does not accurately represent a population. The bias that results from an unrepresentative sample is called selection bias. Issues that can result in introducing bias to a statistical sample include the timing of taking the sample, the length or size of the sample, the level of difficulty of the question, undercoverage of the population, non-responses incorrectly used in a sample, voluntary responses incorrectly used within a sample. Enough about bias. Let's move on to the next part, where we will cover statistical variance. In statistical theory, the concept of variance is defined as the expectation of the squared deviation of a random variable from its mean, or, in other words, it is a measurement of just how far a set of random numbers are spread out from their average value. The practice of the analysis of variance involves a data scientist evaluating the difference between two figures. Typically, this process applies financial or operational data in an attempt to identify and determine the cause of the variance. In applied statistics, there are different forms of variance analysis. Variance and the analysis of variance is a big topic within the field and study of statistics, where it plays a key role in the many statistical practices. As a data scientist, when you are speaking about the process or practice of analysis of variance, you are speaking of ANOVA. ANOVA can be understood as an assortment of methods that are used in the investigation of found or potential differences or variances amongst group means and their accompanying procedures. ANOVA is studied and used in the field of statistics in 3 distinct styles. These styles are determined and defined by the number of independent variables a data scientist is working with or interested in. One-way ANOVA deals with just one independent variable. Two-way ANOVA uses or focuses on 2 independent variables. N-way ANOVA when the data scientist is interested in more than 2 independent variables. Noise. Noise, or statistical noise to the data scientist, is the popular expression for acknowledged amounts of unexplained variation or variability in a sample, population, or data source. Outside of statistics, people often use the term statistical noise to dismiss any data that they aren't interested in. Within statistics, though, when a data scientist acknowledges the presence of noise within a sample, it means that any results from statistical sampling might not be duplicated if the process were repeated. In this case, the sample may become noisy data and rendered meaningless because of the existence of too much variation. Over time, the term noisy data has grown to also refer to any data that is not machine readable, such as unstructured text, and even any data altered in some way that is no longer compatible with the program used to create it. Some of the most commonly accepted examples of statistical noise include Gaussian noise, shot noise, and white noise. Enough of this noise about statistical noise. Let's move on to learners. One can say that the computer or model could improve its performance with more experience, and could improve learning at some rate. Thus, a data scientist will label a computer or model, the learner, as a weak or strong learner based on its performance, or its ability to predict or guess outcomes. So, what qualifies a learner as weak or strong? A weak learner is one that, no matter what the data looks like, will always perform better than chance when it tries to label the data. Weak to strong. Better than random guessing is fundamentally the one and only prerequisite for a weak learner. So, as long as an algorithm or model can consistently beat random guessing, applying a boosting algorithm will be able to increase the accuracy of the model's predictions, its performance, and consequently convert the model from being a weak learner to a strong learner. Take note, data scientists agree that increasing a model's predictive ability or performance even to ever so slightly better than random guessing results means success. When a data scientist considers the options for improving the performance of a model, numerous factors need to be considered. These factors include model bias, processing time, and complexity. At this point, we have covered all of the topics most pertinent to boosting.